In the 1990s, there were a lot of different network standards, computers, and operating systems. There were even multiple different types of Ethernet. The problem was there was no standard way to communicate between these networks, operating systems, and computers. People wanted to share data, but this was very complicated to do at that point in time. And this is where the OSI model came in. OSI stands for Open Systems Interconnection. The International Organization for Standardization realized there was a problem, so they created the OSI model as a guide in order to describe how networks work. This model describes the network protocol stack, which is a set of rules describing how data is communicated through the network. The OSI model consists of 7 layers.
The first layer is the physical layer. This layer is the physical interface between devices. This part of the model you are able to touch and see, unlike the other layers. This layer could consist of things such as cables, frequencies, and connectors. The second layer is the data link layer. This is in charge of activating, maintaining, and deactivating a reliable link between local devices. The third layer is the network layer. This is in charge of delivery of information, including routing and logical addressing. The network layer has the duty to find the shortest path to the destination on the network. The fourth layer is the transport layer. Its duty is to guarantee end-to-end delivery of data. It is in charge of reliability control between the end systems, such as hosts and computers. The control must include no losses, no duplicates, a specific sequence, and good flow, and it must be error-free. The fifth layer is the session layer. The job of this layer is to control dialogues between processes. This includes establishing, managing, and terminating the dialogues. Examples would include login rights and permissions. The sixth layer is the presentation layer. This layer is responsible for configuring the data. This means it is in charge of encryption in order to log into a secure site, compression, and translation, including converting to binary. The seventh and last layer is the application layer. This layer implements user-required functionalities including the following: email, web browsers, file sharing services, print servers, network drivers, social medias, and etc.
This reference model never lived up to its early promises when it was first created, which is why the TCP/IP model was created. TCP/IP stands for Transmission Control Protocol and Internet Protocol. TCP/IP is a suite of protocols used by Unix and the Internet and only consists of 4 layers. It was created by the US Department of Defense because they saw a need for a more simple and more practical model than the OSI model. The TCP/IP model became the most widely used and is the de facto standard. The first layer to the TCP/IP model is the network interface layer, which is in charge of ensuring the physical links. The second is the Internet layer, which is in charge of delivery and routing. The third layer is the transport layer, which deals with the quality of service and other issues including reliability, flow control, and error correction. The fourth and final layer is the application layer, which combines all application-related issues into one layer. This includes the session and presentation layers of the OSI model in this layer.
TCP/IP was not working to its full potential, whereas the OSI model had more layers than it needed. Because of this, a hybrid of the two models was created. The hybrid model consists of the physical layer from the OSI model, the data link layer from the OSI model, the network layer from the TCP/IP model, the transport layer from the TCP/IP model, and the application layer from the TCP/IP model. The hybrid model combines the best features of both models in order to form the best possible model.
The physical layer, just like the OSI model, is the physical interface between devices. This part of the model you are able to touch and see, unlike the other layers. This layer could consist of things such as cables, frequencies, and connectors. Computer 1 uses an Ethernet cable in order to establish a connection with Computer 2. The data link layer, just like in the OSI model, is in charge of activating, maintaining, and deactivating a reliable link between local devices. A very important example of this layer is CSMA-CD. CSMA-CD stands for Carrier Sense Multiple Access with Collision Detection. CSMA is used when an NIC wants to transmit. The NIC must listen for traffic, and if there is no traffic, they may transmit. If there is traffic, they must wait until there is no traffic before it transmits. Collision detection is when there is a collision between two or more stations transmitting at the same time. If a collision occurs, the NICs must stop transmitting and wait for a random amount of time. The first NIC that finishes its wait may transmit, but only if there's no traffic. Although this does not occur in this example, if there are multiple collisions, the wait time is increased each time, and after 16 collisions, the sending NIC discards the frame that it was trying to send.
The Internet layer, like that of the TCP IP model, is in charge of delivery and routing. This includes an important idea of the difference between IP addresses and MAC addresses. When Francois is living in this apartment complex, his IP address and MAC address are as shown. When Francois buys his first home and moves his computer with him, his computer's MAC address stays the same. However, since he's connecting to a different network, his IP address changes. IP addresses depend on the network connection and are dynamic. They change as your network changes. MAC addresses are unique to computers and static. Wherever your computer goes, your MAC address will follow.
The transport layer, like that of the TCP IP model, deals with the quality of service and other issues including reliability, flow control, and error correction. Flow control is the process of managing transmission rate between two nodes. This process is put in place to ensure that one node doesn't get overwhelmed by the amount of data being transmitted. One node will send over bits of data in manageable chunks. Once the data is sent, the first node will wait until it receives verification from the other node. The receiving node will then tell the sender node how many more bits of data it can process. This occurs until all the data is transferred. We can explain flow control by using an example from everyday life. Have you ever tried to jot down someone's phone number as they quickly say it to you? Sometimes you can only catch the first couple digits and have to ask them to re-say it. This problem can be mitigated by asking the person to say the phone number in chunks. Hey, can you give me your phone number so I can call you about the computer science project?
Yeah, my area code is 302. Did you get that?
Yup, got your area code. What are the next 3 digits?
454. Did you get that?
Yup, I got it. What are the next 4 digits?
9040. Did you get the whole number?
Yup, I got all of it. Call you later.
The application layer combines all application-related issues into one layer. This includes the session and presentation layers of the OSI model in this layer. Jimmy wants to send a message with classified data to Johns. He needs to make sure that the data doesn't fall into the wrong hands, so he encrypts it by using the public key. He then sends the encrypted message to Johns. Johns decrypts the message that Jimmy sends him by using a private key. He is now able to unlock the message and reads what it says.
I hope this video helps you understand the different models, the layers of these models, their functions, and how they interact.
No minifigs were harmed in the making of this video. Love, the Happy Team.